recording, and so we're very glad to have Henrik Winther talking today from the geometry group. So maybe I'll let him introduce the title of his talk himself.
Right. I'm going to talk about a joint project with Mathematica and Keegan Flood, who are also from here. And unusually for our research group, it's in non-commutative geometry, and we are pretty much the only people doing something like that here. And non-commutative geometry is a generalization of differential geometry, where you generalize the algebra of smooth functions on some manifold to an arbitrary unital associative, possibly commutative algebra A, and you try to make all constructions agnostic to what algebra you're actually working over. However, in the event that the algebra is commutative, you should reproduce the commutative constructions. So what we are trying to do is to produce a construction called the jet functor from differential geometry, which assigns to a vector bundle the k-jet of its bundle of its space of sections. So the jets of sections of a vector bundle, so order k. So start with a little dictionary. So commutatively, you have the algebra of smooth function. Non-commutatively, we have an algebra A, which is unital and associative.
By the way, Henrik, you're speaking pretty loud, but if you could really shout out, it would be great. Just the volume on this isn't brilliant.
I'm sorry.
No, it's...
So, I'll try to talk to Mauro in the corner.
Okay.
Okay, so we have vector bundles E, and by the source-1 theorem in differential geometry, a vector bundle is equivalent to a projective and finitely generated module over the algebra C infinity M. So you can go to modules like this, but we're not going to use this notation. We're just going to say that the module is the generalization of a vector bundle. So it's a notation that we will use. And instead of projective and finitely generated, we'll usually be working with flat modules over A. So it's somewhat weaker than projective, was used classically. So first I'm going to have to talk about some preliminaries, which is not our work. You can find it in a textbook. The first is some structure that exists for such an unital associative algebra. It's called a first order calculus. So we have a pair omega 1b b, where omega 1b is an A bimodule. And this is notation for bimodules. If I omit one of them, then it's only a left or a right module. We have a map, which goes from D to omega 1b, and it's a differential. So D of AB is equal to ADB plus DA dot B. And note that we are not necessarily commutative here, so left and right module structures are not equivalent, so you cannot switch order of these things. So it's a non-commutative derivation with values in omega 1. And finally, we have a surjectivity condition. Which says that the values of V generate omega 1V as a left module. And by this Leibniz rule, that means that it also generates omega 1V as a right module. So you can switch the A to the other side if you want. You can use the Leibniz rule to rewrite a left product, a right product, with possibly different terms. So, for example, you have the universal calculus, which is actually the universal object of first order calculi. And there the space is going to be the kernel of the multiplication map as a tensor. So dot is the multiplication map in A now. And this tensor product is just over K. The algebra is over some field at the moment. So this is also over the field. And you might be thinking, well, what if there are no zero divisors? What's actually in there? Well, most of the stuff that's in there looks like values of the universal differential. So you have du, which takes some element A, to 1 tensor A minus A tensor 1. So when you evaluate this, you get A minus A, so it goes to 0, so it's in the kernel of the map. And you can check that it satisfies the other properties of the first order calculus. Okay. So proposition, the universal calculus is the universal object for calculi. So for any other calculus, you have a surjection. And this surjection has some kernel, which we call MD. And differential calculi are characterized by their kernel in the universal calculus. So in particular, this PD is a bimodule map. And that's also the reason for this kernel property here. If this wasn't the case, then taking differentials wouldn't commute with this bimodule map. So another example. You want to go to classical geometry and see the connection. What is MD for that? Well, there it's generally, if you are looking at some trivializables or contractible subsets, so you have local coordinates, then it's generated by elements on the form. Of this form, right? Because in the Durand calculus, these are just the same element. This is just another way of writing the but in the universal calculus, they are absolutely different. So you should take the bimodule that's generated by this kind of thing inside of the universal, and that will be the MD for the Durand calculus on some contractible neighborhood. Okay, so if you have a first order calculus, you can extend it to an exterior algebra, which is just a differential graded algebra that has A as its zeroth order term, and omega 1 as its first order term. So any BJ will do, but in fact there is a canonical choice, which is the maximal prolongation of the first order calculus, which is why we encode all our data in there. Because given the first order calculus, you can take the maximal prolongation, which is also like a universal object for exterior algebras associated to that first order calculus. And it's basically the tensor algebra quotiented by everything that you need to make d squared d0. So the minimal possible relations.
Sorry, I don't understand the definition. So what did you just define? So you say an exterior algebra is a differentially graded algebra. That period?
With these properties. An exterior algebra, well, for A and omega 1.
For n, okay.
Yes. So it's a differential graded algebra extension.
Okay.
This is like just the first degree of the differential graded algebra. And then if you have higher ones, it's an exterior algebra. And you should have d squared to see it differential graded algebra. So anyway, you can just take the tensor product. Over A times. Let's say 0 times means that you get this thing. And then you quotient by some relations, which are precisely what you need to get d squared equal to C1. Let's write it like this, but it's important that we have the graded likelihood. And the product in there is going to be called wedge. So
You didn't mention that the surjectivity condition has to be satisfied for the exterior algebra.
Yes. This is for first order calculus. Right? So the surjectivity condition should be satisfied.
By which you mean that omega 1 use A to be A? Okay, yeah.
Yes. Yeah, so all of this is just extensions of first order calculus, not general, not more general stuff. Not this related. Okay, so example continued. The universal exterior algebra is just the tensor algebra. So wedge there coincides with the tensor product. So here the product is also what is generated in the product of the adjacent quotient. But in this case, it's actually just tensor algebra. And D is extended by this rule, but it doesn't give any implication for the product. Okay, so that's the preliminaries, which you can just look at in a textbook. From now on, I'm going to talk about our constructions.
Can I just ask one stupid question? I mean, you have a first order differential calculus as a sort of one term chain complex or something.
Yeah, it's the
and is the second order then correspond to a sequence of length 2 and it just goes on like that.
Yes.
And then you look at extensions.
Yes. Yes.
Okay. Thanks.
So you just have a derivation with values in some module and you want to extend it to a chain complex. So in particular, this example is for the round chain complex, for example, and the round complex. So first, we want to introduce the quantum symmetric forms. And let's say that x0b is again a, x1b is equal to omega 1. Right, we are now working with some fixed first order calculus and algebra. So for this, we have these definitions, and then S2b is going to be the kernel of the wedge map going from omega and tensor omega to omega 2. In the sense of the maximum prolongation. So this is meant to generalize the classical symmetric forms. And now we want to generalize to higher k. So let's say that skd is the kernel of the quantum symmetrization of the tensor product of the lower symmetric forms with 1 omega. And I just use the same letter wedge, but now wedge is going from omega 1 tensor s k minus 1 to omega 2 sk minus 1.
So K form is an element of SKD,
Not a K form, a symmetric.
Yeah, it's quantum symmetric K form is an element. That's the definition. It's an element of SKD.
All right. So this is important because it generalizes the results in classical differential geometry that partial derivatives commute. So when partial derivatives are defined, they will not give a symmetric tensor, but they give a tensor that's inside this space, which is not necessarily symmetric. In fact, if you do this for purely odd supermanifolds, for example, then it will be totally antisymmetric. So you get minus over the change. And it can be anything in between. It's very complicated.
Okay, is this already new work?
This is new.
Okay.
Right. So now we can define jet modules. I'll define them first, and then we'll work the rest of the lecture with constructing them. So we say that a module JKE left the flat module, flat A module, is a jet module if it satisfies the K jet exact sequence. So this is in particular a K jet module.
You got an omega.
Yes, sorry. Thanks, Steve. That's why I wanted to. So jk minus 1 should be another jet module. And then jk fits into this sequence for some jk minus 1, k minus 1 jet module. And in addition to this, we should have a prolongation map. Okay, this is the K projection. And this JK doesn't need to be a module map, it only needs to be a K-linear map, which goes to JK. And such that it is a section if you just compose all the jet projections. So if you go all the way down to E, J0 is E itself. Should be the other way around.
Sorry, silly question. Just sorry, in the definition you say module JKE is a jet module, and then if you have the short exact sequence, what do you have JK minus 1 there as well?
We define them iteratively. So you say that J0 is E, then we define J1. And J1 is something for which the first exact sequence is defined. Now this term is defined, this term is defined, and we are defining this term. So this will be S1, which is omega 1. This will be just E itself. And then we are trying to construct this. And then once that is constructed, we know what should be the two jet modules, and we try to construct that and so on. So we have to work inductively.
Okay.
From zero.
But so a two jet module involves a one jet module?
Yes.
And he was an arbitrary bimodule? Or?
No, not arbitrary. The surjectivity condition is very important.
Wait, but what was
E. No, E is not a bimodule. E is a left flat A module.
Okay, and that is part of, so you define jet module with respect to an arbitrary such flat.
Yeah. So it's a K jet module for E.
So could you say like a kth jet module JKE is a K minus 1 jet module plus another module and a short exact sequence? Is that incorrect formulation?
They can split, but they don't do so canonically generally. Well, this is the definition for some jet module. Now we'll make some construction of some particular jet modules.
Okay.
Henrik, maybe there was a misunderstanding. John didn't mean that JKA is the sum of the two terms of the two outer terms, but that the structure is the structure of a K minus 1 module and then something more.
Mm-hmm.
Like with its short exact sequence.
Yes.
Yeah, that's correct, right? Yes. Okay.
Yeah, no, that's just.
This is a class sentence.
Aha!
Yeah, I thought you meant direct sums.
No. I just mean together with.
I think you have the exact sequence.
Yeah, okay. Thanks.
It's some extension. All right. So. Universal one just for A. More or less by definition, we have that these terms are given by the dot here and the canonical inversion here. So this is just omega 1u. So this already automatically satisfies the one-that exact sequence for the universal calculus. And so that's what we'll get. We'll say that the universal one-that for A is this.
That's also J1, it's a little J1.
Oh, yeah. Yes, thank you. So J1 is given by A is mapped to 1 times A. And it happens to be a right module map as well. This is a bimodule in general. When you're working with A. When you're working with E, it's just a left module. For A, it will be a right map. So now we want to construct the one-that for generic preparatory calculus. Can you read it or just people?
So geometrically this would correspond to trivial line bundle, or this is for functions, right?
Yes, it's the vector functions, exactly.
Yeah.
But for the universal calculus, there's no geometry involved in the universal calculus, since you can tutorially construct it. You need some extra data to really get geometry. Something like the around calculus, and then it will be nice. But the universal calculus is really degenerate, and we'll see why later. But it's a helpful step to go towards the So, suppose that we have this, and now we have our projection here. So I'm going to go 1, 3. Assumption we have this as an exact sequence. These two are equal. Let's say we have projection over here. Now here we have n. Here we have some. we have this. So now we have some exact sequences, and we can apply the snake lemma to this to get that this is an isomorphism, and this is equal to 0. So, well, let's set this. To be this, and then this all works out. So in particular, you have the wanted exact sequence for B. And then we define the prolongation map. To be just the quotient of the universal prolongation. And whenever I write square brackets, it generally indicates quotients with respect to ND. So you go to the class. And ND is a sub-bimodule, so the quotient is a bimodule as well. Now it satisfies everything we want. This is a commutative diagram. All maps are bimodule maps. So in particular, you get the depth projection here by just taking quotients. We can work upstairs if you want. Right, and this is this universal prolongation map is a splitting operator since it's a right module map. So as right modules, it splits the sequence. This is a splitting operator as right modules as well. So now these are split exact sequences as right modules, but we also need them as split exact sequences as bimodules. So let's introduce them now. Class of A times B goes to ABB. This is a left module map since the left module action is just on A. And gives a left splitting map here. So this sequence splits as both a right and a left module, but not simultaneously as a bimodule. So since this splits both as a right and a left module, our life is very easy because now we can just tensor on the right with the left module, and that will preserve, well, it will preserve exactness of split exact sequences. So you immediately get the left. Apply the Functor tensor over A E to this exact sequence, and then you get the sequence. this, which is exact and fits in the definition of a Jet module for order 1. And in addition to that, we can take the prolongation map. Do this the obvious way. So now this is a Jet module. I will call this the Jet module for you. Right, so this stuff until now preserves regularity. So the regularity of J1E, by which I mean either projectiveness if everything is projective or flatness is flat, will be the minimum amongst omega 1, B, and B. It's just the same statement for flat. So it preserves regularity in this sense. And in particular for one jets, we don't need any assumptions on E. We don't need flatness because this sequence splits in this case. But we will consider it as a functor. So let's say we have a module map between two left modules. Then we can simply take the map between their jet modules. Do the obvious thing. You just conserve the identity and the space. So this gives factoriality, and in particular, because of this, it preserves the full subcategory of flat modules and the full subcategory of projected modules. And also from all of these, we have this I1. And actually, this omega can also be seen as a factor, this multiplication, factoring on the left with omega b. And then this will give you natural transformations between these factors. Okay, so now I will come to the reason why you care about these things in classical geometry. Jets are universal objects for differential operators. And we can also define differential operators that are jets. And at the moment, we only have one base constructed, but that's okay. We can construct first order differential operators, and they will be quite useful. So in classical geometry, a differential operator is something that was a priori defined, and then you constructed jets to work with them more easily. But for us, differential operators are not defined. We will define them in terms of jets, rather, so going the opposite way from the classical story. So now this is not a module map. This is merely a k-linear map at this point, a k-linear map between modules. But it should satisfy right, one more thing I should mention. This will be differential operators with respect to D, to the first order calculus that we have chosen. There's generally no good way to do this for an algebra without choosing some first order calculus. And now this should be a bundle map. And unfortunately, the only thing that we know that should be bundle maps in our general setting are vector bundle maps, i.e. C infinity linear maps. So, or A linear maps. So this should be in A Hans of the A and this and formally I should say that this is a differential operator of order at most k, because it could also be a lower order operator, but it's too long to write.
So are you saying it's just an extension in the category of A modules? E and F are A modules, is that right?
E and F are A modules.
This is an A module map.
This is not an A module map. This is just an okay. So it's explicitly not necessary that this is an A module map. If it is an A module map, then it's a zeroth order differential operator, because this is just an isomorphism.
Okay, sorry, I was a bit. There's two uses of K here then. There's the field. Is that right?
Oh,
sorry.
Yeah, you are correct. Maybe I should switch one of them to N. Yeah.
So K is the underlying field.
K here is the underlying field, and K here is N. Thank you. So confusing. So anyway, the jets are precisely the thing that contains enough information to turn differential operators into bundle maps, classically.
Are these extensions unique, or can there be many?
So far we only proved that they are unique for first order operators.
Okay.
But in classical differential geometry, yeah, they're unique. I'm talking about our setting.
Okay.
The that seems to be related to this, what you call it, this subjectivity condition.
No, I see.
Okay, so first order differential operator are in bijection with C-infinity linear maps. Differential operators between E and M are in bijection with A linear maps from J1 E to F. Corresponds to the classical setting. What we asked about. And secondly, we can characterize them in terms of NB as well. It's a first order differential operator if for some Ni tensor Ni in NB. This vanishes. So it's precisely those maps from the tensor product. That's the that vanishes on the ideal or the sub-bimodule generated by this. Let's see. So this is nice because it gives us something that's a bit more concrete. You can compute which maps are differential operators directly instead of having to go via the jets. So now let's see, actually this is useful for non-commutative geometry because people came here before us. They didn't have a notion of differential operators, but you can't do geometry without differential operators, so they produced a lot of ad hoc operations that should be differential operators in classical differential geometry. All of the ones we tested are differential operators in our sense. The differential itself, D, is a differential operator of order 1 with respect to itself. D connections going from some module. So a D connection is a module, not a module, but a map going from E to there, omega 1 tensor over E, such that a particular Leibniz rule is satisfied. So A is an element of A and E is an element of E. And then it's linear up to this differential term. So that's a D connection. These are differential operators. They're also quite used in non-commutative geometry. And finally, quantum partial derivatives, which only exists when the calculus omega is actually a free module. Okay, so already these are all first order operators. Already it's quite useful. And now we want to talk about jets of order 2 and higher order. Our strategy here will be to construct the jets as the solution space to a differential equation. But not a differential equation on a differential equation on the one jets. So we start with constructing them for the module A over itself. That's the last time. So this is just by definition of a jet module. But we can also take some of the other stuff we have constructed, in particular the jet modules are modules, so we can take the first jet exact sequence of the one jets, and that gives us something that should be related to this. So that will be this notation is for the iterated or non-holomorphic jets. It just means taking jets repeatedly. So you take one jet, and then you take one jet of one jet. Or you two, three will be three times, and so on. You should all have mapped like this. This is an equality. And now we can take a Cover's delta wedge. It's L. We can take co-kernels of this. And now, this is exact, this is exact, this is exact, because this is just an equality. This is exact, and this is exact. And therefore, by the 9 lemma, the bottom is also exact. And so we get this isomorphism here. But this is a space that we know more about. We can construct it in a different way. In particular, we can get it from applying the omega 1 factor to the one that exact sequence. So let's do that. This omega 1b is the omega 1b tensor over AA. So it's just like the middle sequence of there and tensor with omega 1. And now here we have S2b. And this is just a definition of S2, that this goes to omega 3. This is precisely what we have over here. call this map W. And this is just the definition of wedge. And now we apply the 9 lemma again. And we see that this is exact for trivial reasons. This is exact. This is exact. So this is exact. So we have that W is just an extension of wedge. And the map that we actually want, which is going to give our differential operator, so we'll go back to tilde, is an extension of W. But here we have more information because we can actually get a splitting of this, which induces splitting of this. And then we can use the commutativity of this diagram to compute the components of this splitting. And this will be a splitting with respect to left modules. So we have this instead of omega 1, and it's just the action everywhere. And this one becomes alpha wedge d tilde. Okay. Oh, this should be okay, so that's using a left splitting of the sequence, so we just write it as a direct sum as left modules of this and this. But this is not compatible with the right action, and this d tilde should be a bimodule map. So in particular, we can compute the action on this co-kernel space. We will call the so let's see if we have alpha plus omega, where alpha is in omega 1 and omega is in omega 2 times that. And we will use this symbol for this, which we call the sombrero action. And then to make this a bimodule map, this is what you have to do. You have to kind of twist this right action by the differential. But it's okay because the differential is in particular a derivation. So this is actually a right action. And with this left and right action, we're going to call this co-kernel space. We're going to call this omega 1, 3, omega x, omega. I don't know what you think about the notation, but that's all. We also just call it a special place because it's kind of strange. But in any case, with this action, it's visible that this is a bimodule map. And now we just have to extend that map to d tilde.
How much longer do you need, Henrik?
5 minutes. See, it says at least 55 minutes.
Okay.
I think we started a bit late.
Yeah, maybe, yeah.
Alright, so French line coming. This is what you get in the end. So we have written it very compactly using this special version. And this is actually a first order differential operator on the one jets. And we will define we will just define the two jets to be the solution space of this natural differential operator, which is quite interesting because I haven't seen this approach in classical differential geometry, even though you could in principle do actually the exact same thing there. And it's a natural differential operator, so you think you can, at least I never encountered it or anything like it. Right, so it encodes two pieces of information inside itself, which can be interpreted classically. So if you have two different projections going from the iterated two jets to the one jets, one is the jet lift of the projection. We get this by just jetting the whole first jet exact sequence, and the second one is the more standard projection that just comes from the jet exact sequence of the one jet. And these coincide on the kernel of the theorem. That's also a theorem in classical differential geometry. It's good. And secondly, it encodes differential dependence in the sense of d squared equal to 0. So it's kind of like saying that the leading part of your Taylor polynomial should be the derivative of what came before it. And we also have, of course, the prolongation map. Maybe you can guess it by now. Take 2. So you just put ones everywhere except for. And again, it's a right model. I'm running out of time, so I'll just summarize what happens after this. Again, we can tensor the exact sequence for A, and this will give us a prolongation map since this is a right module map. But now we need assumptions for everything to work. So in particular, now we should restrict to modules that are at least flat. And again, you have the property that the jet functor preserves, well, it is a functor, and it preserves regularity. So in particular, it restricts to an endofunctor in the full subcategory of flat or projected modules. Right. If you want to go to higher order, it's clear now what you have to do, because this lets us encode differential dependency between two variables. So you can simply enforce that you have pairwise differential dependency between all variables. So you take the something like the iterated longets, and then you just take the intersection between J2 of J1 and J1 of J2. That should work, but unfortunately, we are not quite done with working out the assumptions that are necessary for it to hold above depth order 3. So I think we should stop there.
Any questions, comments? Yeah, go ahead, Lukasz.
One question, so you said over there that when you define this differential operator, you don't have any other way to actually use a bundle map, but this map of vector bundles. So does it mean that it then incorporates a linear differential operator?
Yeah, that's the problem. If you have more general bundle maps, that's why I leave it on this line. If somebody introduces more generic bundle maps, then we immediately get nonlinear differential operators. But since we only have vector bundle maps, we only get linear differential operators. In the particular case that your E is actually an algebra, it can also be polynomial differential operators, right? In the obvious way. It's trivial.
Any more questions? Online?
Just to make sure I understood the last part correctly. So you're saying instead of you say that computing linear maps from higher jets can be complicated, so you reduce this to just do something easy k times rather than doing something hard for k1, right? That's basically, so you iterate you know what to do in the case one, n equals 1,
yes,
and then you just iterate that thing k times basically, because you can do that k times, and then you get an explicit formula for these higher differential operators.
more or less.
More or less. Yeah, that's exactly that works out for me.
Okay, well, if there are no further questions, then thanks again, Henrik. And next week we have Christoph, panelist, talking. So that's all for today.